I'm Stephanie, and this is the Cool Part Show, a show all about interesting 3D printed parts. Today we're coming to you from Northeast Ohio at JuggerBot 3D to learn all about this part, which is made from 3D printed PVC. This is not a common material to be 3D printed, but it is critical to this application in wastewater management. A 3D printed vortex flow insert on this episode of the Cool Part Show. This episode is sponsored by PT Expo 2026, the event of the year for molders and mold makers. If that's you, join your industry on March 17th in Rosemont, Illinois to experience cutting-edge technologies, breakthrough innovations, and expert-led education right on the show floor. PT Expo is where your industry goes to source, learn, and network in the most manufacturing-dense region of the United States. For a limited time, use the promo code PARTS to score a free Expo Pass to this year's event. Learn more and plan your visit at ptexpo.com, and we'll see you in Rosemont. Welcome to the Cool Part Show, and thanks for joining us. We've seen on many episodes of the show instances where 3D printing allows one material to replace another, but this is not that. The material for this part, PVC, is actually so critical to the application that JuggerBot 3D, our host today, and their customer IPEX had to collaborate closely to develop the printing technology and process in order to work with this material. This is a vortex flow insert. It's used in sewage and wastewater management, typically in places where the liquid is moving from one elevation to another. There's some sort of a drop. The wastewater flows in through the top of this insert, and then the spiral geometry on the inside helps to create a downdraft to suck air into it. Adding air into wastewater is a good thing because it helps to oxidize emissions and reduce smells. There are certain emissions, things like hydrogen sulfide, that can be really corrosive to materials like metal and concrete, and that's why this insert is made out of PVC. So the manufacturer of this part, IPEX, makes these vortex flow inserts in a variety of sizes and shapes, usually customized to the particular application. The design works. This is a product that is very effective, tends to have a long lifespan in use because there are no moving parts. All of the functionality is coming from the material and the geometry, but they were limited in terms of the different sizes and shapes and the ease of customizing this product, which is what led them to look at and explore 3D printing as another production method. So here is Philip Martino. He is the Director of Research and Development for IPEX, which specializes in polymer pipe and pipe fittings.
IPEX produces a wide range of products for various applications. We design and manufacture the world's leading and most recognized and diverse range of integrated PVC and CPVC piping products. And our new R&D center here in Mississauga, Ontario, helps us accelerate innovation, process innovation, and enabling faster product development and quicker turnaround times and time to market for our highly customized solutions.
So piping is made from lots of different types of materials, but IPEX exclusively focuses on polymer, and a lot of that polymer is PVC. This material is so important to their applications that they even produce their own PVC compounds for processes like extrusion and injection molding.
PVC stands for polyvinyl chloride. It's a relatively inexpensive yet incredibly durable and effective polymer. It has many benefits, including its unmatched durability, corrosion resistance, lower energy consumption, and reduced greenhouse gas emissions.
So in the case of these vortex flow inserts, PVC's resistance to corrosion is really important. This product is being made from the right material today. But IPEX wanted more options in terms of the different processes that they could use to work with PVC. As Philip mentioned, they produce a lot of pretty customized components, including these inserts, and they have to make products like this in a fairly manual fabrication process today.
Units are made with over 10 different parts, if you will, typically made out of PVC sheet or pipe. They're bent, they're heated, they're cut, they're glued together in order to make the final unit. So it is definitely a time-consuming and labor-intensive process. And that's where we saw 3D printing as being of real value.
So IPEX saw 3D printing as an opportunity to start to consolidate those assemblies, simplify production by kind of automating it through 3D printing. Using a more digital fabrication process would allow for better consistency across the products, even when they're being customized to the particular application. Just one problem, PVC is not a commonly 3D printed material, and that brings us here to Boardman, Ohio and JuggerBot 3D. JuggerBot is a supplier, a developer of large format additive manufacturing technology, and they've developed sort of a reputation for being able to work with a larger range of materials. So here is Dan Fernbeck, the Vice President of JuggerBot 3D.
JuggerBot 3D manufactures industrial-grade 3D printers that are uniquely capable of processing a pretty wide variety of non-metallic performance materials. We have managed to process over 100 different material types now through our partners, especially some of our partners on the research and academia side. There's probably over 400 or 500 different types of materials that have been processed through our Tradesman series.
So the Tradesman series is JuggerBot's name for its line of large format fused granulate fabrication, or FGF 3D printers. So these are extrusion style machines, but instead of running from a spool of filament like your typical fused filament fabrication or FFF 3D printer, they print with pellets or granulate. The material format actually helps to expand the potential material portfolio because there are more polymers available in granulate and pellet formats than currently extruded into filaments. So FGF works a little bit more like conventional extrusion than your typical FFF printer. The pellet material is gravity fed into a heated barrel turned by a screw that uses heat and friction to melt the material. Pressure builds up inside of the extruder until the material is extruded out from the nozzle. Typically, FGF can print at a higher deposition rate than FFF, which makes it a great fit for parts like this that are on the larger side. It also turns out to be a pretty good process for the PVC formulation that IPEX was already working on for additive manufacturing.
We began exploring 3D printed PVC back in 2018, knowing that we needed alternatives to our current 3D printing methods. We wanted compounds that have the same characteristics and capabilities as our molded or extruded materials. So we started in 2018 by developing our own 3D printed PVC compound, which is a bit unique than injection molding or extrusion compound. And we began working with JuggerBot around, I'd say, early 2021. We had the material side figured out. I mean, we had the nucleus of it, but of course we needed a partner in order to validate what we were designing. We didn't have specific 3D printers that can process it, yet we thought we had a pretty good idea that it would work.
So at the outset of this project, IPEX understood the application and the material very well, but they needed a 3D printer and a process for working with this material additively. From JuggerBot's perspective, they're the experts in the 3D printing process, but they had to come up to speed with working with PVC and the requirements for the end-use parts that would be made this way.
We didn't really start making real progress on machines and capabilities that were a good fit for PVC until one of our customers and partners, IPEX, came along. After basically going through some trials with them and better understanding where their needs were, we had set out to create a more off-the-shelf printer with the provisions and capabilities in place to safely, reliably, and effectively process PVC grades or similar types of materials.
So this is kind of an interesting case where it wasn't material availability or formulation that was holding up additive adoption. It was really an issue with hardware and software. Getting to a 3D printer that can effectively process PVC is not perfectly straightforward because this material can be a little bit tricky to work with. But IPEX has a lot of history with extruding PVC, and some of that experience and expertise carries over into 3D printing as well.
3D printing PVC is similar to extrusion in many different ways. I mean, first of all, you need to have a certain melt temperature for it to flow. So that would be the first thing. We need the same material requirements, so stainless steel type screws and barrels to make sure you minimize on corrosion of the equipment. PVC extrusion a little bit different, on the other hand, because it requires dies and pins and bushings, for example, in order to extrude. And then in 3D printing, of course, you need certain heated chambers, a certain temperature of the chamber, certain bead sizes, widths, and heights in order to minimize any sagging or the optimal placing of the PVC beads and layering the PVC beads.
There are some inherent challenges in processing the material itself. And those stem both from a standpoint of how the machine needs to be constructed, as well as what kind of safety provisions need to be in place to make sure that operators are safe, that the environment is protected, and that the machine is not going to fail sooner, or wear out, be damaged to limit its life expectancy.
So Dan mentioned safety as part of the processing requirements here. Working with PVC can pose some risks, primarily if the material is overheated. If PVC burns, it can off-gas a handful of chemical pollutants and other gases that could be a health hazard or corrosive to other materials in the environment. So you want to make sure that you're processing it appropriately. IPEX has been working with PVC and extrusion processes for a long time. They have the appropriate equipment, the safety measures, the procedures in place to make sure that it's consistent and safe every single time. And both parties wanted to make sure that they were developing a 3D printing process that would be just as safe and repeatable and reliable. So one result of this collaboration was that JuggerBot actually created a special model of its Tradesman Series P344 called the Astra, which is customized and has some special features particular to this application.
We took a lot of time up front, our team did, in understanding, first and foremost, what types of different grades of PVC were out there, and then how the specific types of PVC that IPEX wanted to run needed to be handled. So we're taking into consideration things like the melt temperature, the residence time, in how that even, I think, transfers to part performance. So a big point of our emphasis with all materials, PVC included, is capturing the optimal layer time window and then building that into the essentially the software part of our machine so that it's very much a data-driven process. I think one of the big points of focus our team has put on over the past 2 years into that system, and where some of the more unique challenges has come to play, really stem around some of the fail-safes that have been built into the system. And a lot of that is a connection of the hardware and the software for things like timeout sensors and again, safety provisions to keep operators safe, to make sure that not only are they, when they're trained, that they're operating safely, but that common accidents are thought of and mitigated ahead of time, right? So really thinking about what could go wrong, even if it's not meant to go wrong, and how can we prevent that from being a catastrophe.
So avoiding catastrophe. Here's one example of how that plays out. Some cars have a feature called a governor that limits the maximum speed of the vehicle. The Astra 3D printer has a feature in its software that basically prevents the operator from burning the material. It's sort of a governor on the temperature of the polymer that's about to be extruded. There are also other controls, like for instance, you can't open the door immediately after finishing printing. You want to make sure that the gases have time to be extracted from the build chamber. And there are various other little bits and pieces around the hardware and software of this machine geared at ensuring the safety and consistency of the process. So this vortex flow insert and other early iterations of the part were produced here in Ohio by JuggerBot 3D. But IPEX just recently took delivery of their first Astra 3D printer, so they'll be able to produce inserts like this and other products at their facility in Canada.
I think the main benefit is the vortex flows today are designed based on the fabrication process. So we have a sheet that's bent, or sheets that are bent, and we have pipe. So there's not much customization that can be applied, but which could be applied now with 3D printing. That's what allows us to optimize material usage, for example, to optimize fluid flow, because now we can customize the design for the fluid flow that's intended for the system.
To fabricate a vortex flow insert of this size and shape previously would have been about 6 or 7 different parts assembled together in a process that could take about 80 hours. With 3D printing, one of these can be made in about 20 hours, which is a pretty substantial time savings. After printing, a flow insert like this would require drilling and a polyurethane coating, but these steps are the same or very similar to what IPEX would do with a traditionally fabricated PVC insert. 3D printing allows the production process to be faster and also more automated, which is important as manufacturing continues to run up against an ongoing skills gap. So right now, IPEX is still in the development phase. They are evaluating different designs, different products, looking at potential cost savings and time savings, but it's going well. From JuggerBot's perspective, they will continue to collaborate and work with IPEX as needed, but they are also pretty excited about the potential opportunities for 3D printing with PVC in applications like this one and beyond. So to recap, this is a vortex flow insert designed and now manufactured by IPEX. It is used in wastewater applications to help aerate the water and reduce emissions. Previously, a part like this would have been fabricated from multiple pieces of PVC that had to be cut, bent, joined together in a process that could take as much as 80 hours. Now, using 3D printing, IPEX could potentially 3D print an insert of this size in about 20 hours, which is a significant time savings, as well as a reduction in the amount of labor that is required. 3D printing also opens up opportunities to better customize and optimize these inserts for their particular application. That's it for this episode of the Cool Part Show, but thank you so much to JuggerBot 3D for hosting us here in their Boardman, Ohio facility. If you want to learn more about fused granulate fabrication, printing with PVC, or anything that we've discussed today, check out the links in the show notes. And if you have a cool part that you'd like to see featured on the show, email coolparts@additivemanufacturing.media. Thanks for watching. This episode is brought to you by Manufacturing Connected, the new home for the Cool Part Show. Manufacturing Connected is a platform from our publisher, Gardner Business Media, where we share actionable insights for manufacturing business leaders, regardless of the processes you use or the industries that you serve. We're covering everything from automation and AI to tariffs and workforce management. Go to mfgconnected.com to sign up for our weekly newsletter. In every Tuesday issue, you'll find quick reads with clear takeaways, access to in-depth interviews, and useful links about the issues that matter to your business. Get connected today at mfgconnected.com.